Hello, my name is Frank Marfai. I am your course instructor, and I'm so happy to be talking to you today about the group project, which, as you know, is right now a big question mark. Like, what is it all about? So I'm going to give you a little bit of outline of what is expected of the project. So you've been learning calculus for a while now, and you might be wondering, what do you use it for? Or how can you use it in the real world? And you saw a little bit of that in chapter 5. And this group project is going to give you a chance to do that. And when I make a group project, it will be a small group, meaning like 2 people, maybe 3 at most in a group. And really, it's going to come in a couple of stages. There's a common element that everyone is doing, and then there will be something specific that you choose what it is. If you are finding trouble finding a partner, let me know. We'll put you with like-minded peers who are interested in working on the same project. You'll get to choose what group project you're going to be doing. So let me talk a little bit about some of the concepts that are being covered in this group project. One of the things is when you look at real objects in the world, let's say we have this over here. Okay, and this is taken from a magnetic levitating toy that you see here. And it does rotate. So that really is a solid of revolution. Okay. Or maybe you're trying to find where the balancing point of a toy eagle is. You see here. So for example, I can take this toy and mathematically it's actually right, the balancing point is right where the peak is. Now, how did they shift the mass enough just to make that happen? Now, in our case, we'll do a 2-dimensional version of this. Maybe this is an eagle printed on a poster or something like that. But where is the balance point for this eagle? And can you find it? What about this? Let's say you want to manufacture a glass and you want to figure how much glass is it going to take to do this radiometer. Now, this radiometer, if I move it, maybe not, but it is actually light. So if I were to turn on the light here, what would happen is this would rotate. Works better than advertised, we think, right? But on a bright sunny day, what you'll notice is this actually starts rotating quite a bit. Actually, now it's rotating when I'm trying not to have it rotate. Okay. Or what if you're trying to figure out the volume water that would fit in here? Or what if this is solid? What is its volume? This is actually a fruit container that holds lemons, for example. It's something similar, which is for vegetables, which is holding an onion. But let's say you were to manufacture this. What would it look like? How much could fill this in there? Also, we have shells. Or, let's say you want to manufacture a guitar. Each one of these does represent a project, and what you will choose is which one you want to study or model. There are a couple of steps to it. So really there are 1, 2, 3, 4, 5, 6 projects to choose from, depending on what interests you. Each one will have a description for the project, but before we even begin any project, let's talk about how do you model things. We learned the mathematics, but we don't, there's no equations provided for any of these objects that we see that are around me at the moment. So a couple of things we do is we do make measurements, and you will be given those measurements of it. But first thing we want to do is to know how to do curve fitting. So what I will be doing is scanning these a little bit later today and showing you how I'm going to create an assignment, which has to do with you are going to figure out what is the polynomial curve that goes through those points. Notice I put absolutely no labels on this. You're going to have to make your own coordinate system. What I can tell you, though, however, is that each of these grids is 1/2 centimeter by 1/2 centimeter. So 4 of these grids altogether produce 1 square centimeter. That's something for you to know. And then here, the first trial, I'm going to ask you to create a coordinate system. And I'm going to ask you to do a curve fit of a polynomial with degrees either 2, 3, 4, 5. Test them out. And which one do you think will fit best through those points? Now, again, you need to create your own coordinate system first. So that's using one polynomial function. But sometimes doing piecewise, where you change the definition of the function, because if you look at it, you can almost imagine seeing two different functions here. And looking at this, maybe you stop here and then you continue to make a new function. But there are many choices you can make. And what you are doing is splicing two different functions together. This is actually a theory behind oftentimes you will see multiple functions merge together to create artistic fonts, for example. There's more I could say in it, but I also want to make sure I don't talk too long on this introductory video to the group project. Lastly, I'm going to give you this curve here, and I'm going to be asking you to find a polynomial equation through that best replicates this curve. And this is, again, as an introduction to the project. Ultimately, after finishing those 3 steps, you will have the math skills to then begin creating your own, picking the shape that you want to study, and then modeling a equation through the points that you end up sketching for perhaps it's the eagle, looking at it from this perspective, or perhaps it's the solid revolution. Whatever you choose to pick will be the one. Each will have its own set of instructions, and it will be very exciting, I think. You'll find out how to really apply this. When you think of 3D printing, all those molds and casts, there are equations in the background that determine it. So the question is how much polymer resin do you need to actually to fill them? Or if you're doing it with metal dye is the same idea. So you're going to be creating the best as you can, equation, a polynomial that goes through this. Part 1 of this curve fit will be to use just one polynomial, do your best. Part 2 is split it into maybe a few functions and see what really works best for modeling it, and then create a piecewise function that describes this. And then what I'll ask you to do is, using whatever software tool it is, you can use Desmos, you can use other types of tools that will be on the list, but showing visually what it actually looks like on the computer. So there's going to be a lot of computer modeling. In this particular section, especially when you're starting to work with real things, many of the techniques that you know how to do by hand, you'll be using some computer assistance, because if you have an 8th degree polynomial, and that is what's squared when you're rotating it, that is not a very pleasant thing to do by hand. But we do have software tools that can help. You already have worked through the concept of theory of how to do many of these. You're going to be applying it to a real life situation now. After you go through and do the find the equations, what I'm going to ask you to do is to pretend that a coordinate system is attached to this somehow. I give instructions, and then I imagine you say rotate this, and either find the solid revolution, secondly find the surface area revolution as well. Okay, that is a quick introductory component to what's coming up next. I'm very excited for what this is going to be. So again, think about it a little bit. You'll be actually making a decision on which object you want to study. So everyone's going to have the one about learning how to do curve fitting. It's one of the skills that is not taught in a calculus class, but is one of the most useful tools you'll have when you're doing applied mathematics and making applied problems in it. So, and this really is the basis of other modeling applications that you will see. Piecewise functions is super helpful. Merging functions together. If you're ever interested in something called Bezier curves, there are some certain rules of how you would put things together. Or splines, that's another one. So onion, that'll be one option. Finding the volume of this, or find the volume of this lemon. Each has its own unique challenge that you're going to have to overcome. You'll see when you try it. Or finding the volume revolution of this, or finding the volume of this rotating cylinder, or either finding the volume or the surface area of the radiometer. And now it works just fine, right? And I've shown a light on it, didn't work. Or the eagle. We'll approximate the eagle in 2 dimensions, and there is a way to prove this as well. Or, let's see, so the eagle's there, did the radiometer, or you'll be finding the body of the guitar. Again, this does require, what's nice about some of these is there's a lot of symmetry inherent in many of these objects, which will save you some work. As you're preparing for the group project, what you might want to go back and do is review some of those solid revolutions that you did earlier in chapter 5, and also the surface area revolution. If you decide to go with the center of mass and trying to find the balancing point of this eagle, you might want to also review how to find centers of mass. Center of mass is even funnier. And that's going to be it. Hopefully I did not ramble on too long. I hope you enjoyed. If you're in class, you'd actually be able to touch and hold these objects. And I would have a bunch of rulers and tape measures that you guys could go and do your own measurements. Unfortunately, in our situation, we don't have that capacity. So one of the limitations is it's only as good as the photos that I made of many of these objects or the drawings that I had cast or tried to cast of these objects. So there might be a little bit of error when you're approximating, but there are a couple of, be confident that if you do the math right, the math will prove the physical properties and the physical properties will verify the math. Both will happen. Right. I look forward to working with you and to be continued. All right. Have a wonderful evening.